discuss about the due date. Now, you know that actually I have something like the open due date policy. That's something new actually. In the back days, well, last semester or semester before, I used to have something called 72 hours extension. That means if the student need more time to work, they are going to have 72 hours without, don't need to ask a permission for it. And this actually worked very fine. But now, I think it's worse than what we had during the COVID. Now the student need to go to school, some of the activities and doing the rest from home. And that's actually, for my side, I think it's more than doing everything or everything on. So the due date, as I discussed with you earlier, is going to be an open and certain time. That's means we usually have the due date for the assignment number 1. It's at the week number 6. Today is week number 4. And but what I'm going to do is I'm going to put a poll on the teams. If the student said, okay, now we are ready, we need only 1 week to go, then I'm going to set the due date for the assignment. Other students said, oh no, we need a little bit more time, then I'm going to give an extra week or something like that. It's going to be flipping thing, but believe me, it's going to be more comfortable from your end. I know that some students would like to have a specified due date to say that we're going to follow and submit, and we're going to have a pressure, a motive will let us do the work. I'm going to do something like that, so it's not going to be infinity time. I will say, okay, by the end of the week number 6, you should have all the students be submitted, unless if you are going to have an excuse that need to have an extension for it. Now let's go to take a look for the material we had earlier. We first opened that earlier, the videos. The result now is available for you. I added 8 sets for the shear box results and for the sieve test results. How to use these sets? You go to this list, and here I get to have the allocation for the student according to their names. So you can see here, for example, that Dominic is going to have the sieve test set number 5 and the shear test set number 6. That's how it's going to work. And according to your name, you will find what set you need to use. Some of the students are already withdrawn the subject, but that's in general for all the students. That's how you're going to use the sets. Now, about the calculation process for these sets, we are going to run during this week another tutorial on how to do the basic calculation for the results we got in the 2 sets you are going to allocate per each student. What you are going to have actually in these sets is going to be an Excel sheet, and this will be a good chance actually to do the whole calculation by using the same Excel sheet. Then take a snapshot for your results and copy the graph and put it on your Word document, which is going to be the lab report. The lab report contains discussion, introduction, discussion, and conclusion is going to be based on a research. That means you will go online, search about these topics, try to find some references, and use them to build your report. It doesn't have to be 20 pages. Every report, we have 2 sections. Every report, let's take something between 3 to 4 pages without the graphs and the tables. Okay, so in total, we are going to have let's say 6 to 8 pages per the full report for the 2 tests. I'm going to upload some of the material I already have, and this will help you a lot to build your work. But once again, it's going to be your duty to find extra material. For the week number 4, today we are going to start to talk about we understand the characterization of the material and how we can specify the material properties, we're going to start now with selection of the material handling system. And the first thing we're going to start with is going to be about the district material. That's mean I'm going to have a factory that making the filling for water bottles, and then I'm going to make them in boxes, and the box is going to be as a pallet, and I need to move them around. We talked about this one briefly in the introduction lecture. I'm going to bring some of the material from the first lecture today, and we're going to introduce later about the AGV and the retrieval system, the storing and retrieval system. And I think that you already know a little about these two topics. We're going to give you a brief calculation on selection of the number of vehicles we need for the AGV system. We're going to start with the basic thing, and also the same thing is going to be for the calculation of the time required and the efficiency for the retrieval and the storing system, like having the aisles, and the machines will do the storing and retrieval for the material from the aisles. Just remember that in any subject, we don't give you a full meal. We give you just a sandwich, and yourself need to search and find the rest of the knowledge you need to know about this thing. Now, basically what we teach you is what's going to be enough to understand the concept of the technology and the application. The rest about the detailed design procedure, that's something is going to be for the specialized people, and that will be something you get to learn during your internship or during your let's say what you call the training period in your company. What I'm going to do actually is I'm going to have a contact with some of the students who actually found jobs based on this subject. I know at least 5 of them still connected with me, and I was their references while they're applying for the jobs. But of course, we have even more, because I thought that this subject used to have something between 150 to 200 students per semester, but things now it's changed because of the lack of students. I will try to bring one of them, and he will give you a brief talk about his experience, and I think that will basically give you some help about finding your way in the future. The week after, we're going to have the pneumatic conveying system of the bulk material. How to use the air pressure to move the materials inside the pipes. Mainly this material should be light, so it can be carried by the air. The week after, we're going to have the hydraulic conveying of the bulk material. These two topic, the week 6 and the week 5, are going to be the core of the assignment number 4, yeah, because this will be assignment number 3. The assignment number 4 is going to have 2 sections. The first one is going to be running online, and because this semester we're going to have the student back, then we're going to have the Easter holiday, then we're going to have the Anzac Day. We're going to lose 3 Mondays. Let's make an agreement on how to substitute that. That means that the tutorial assignment is going to be running another day rather than Monday, because Monday is going to be a holiday. The assignment is very simple. We are going to give an example in the class. We are going to have a tutorial on this example, and then I'm going to give you a 1-hour window for the quiz. I send you the question sheet. You are going to work from home, and then you will send me back the assignment papers with the solution after 90 minutes, for example. You are going to upload normally to the Canvas, and I will do the marking for it. This will be a good practice for the final exam, which is going to be once again a take-home exam. But the other one is going to have 6 hours windows where you can do the solution for 4 questions or 5 questions and send it back to me. And once again, just remember that during these sessions, I get to be with you all the time to provide the advice and the help. So we are going to go back to today's lecture. And also what I have in this material is the question number 3 for assignment number 1. We covered that last Wednesday, but still it's going to be a good advantage to have a copy of what we've done last year. Is now available for you. The lecture recording is going to be available here after going to refresh them with a new recording. So let's go now and let's cover the slides that were available actually for you since last week. And the topic for today, as we mentioned once again, is going to be the first material handling solution, which is the the discrete material handling. How to move the material as a unit load. Can anyone here remind me what the unit load is? What the unit load?
Like a pallet.
Exactly, like a pallet, like a bag, like a boxes. Okay, so we can simply put the material, pack it in the boxes, and then this will be much easier to be moving. So this will be topic for the lecture number 4 subject. And once again, just to remind you about what the material handling technologies and the role in the, sorry. Oh, I just remember that was one of the students asked me to approve his, he's not here. Okay, actually someone told me that he applied for joining this. Okay, anyway, he's not here. Maybe he's already got the access. Yep. So we said that the material handling process is one of the activities we have in the manufacturing processes and the production processes. It's not part of changing the product or making the product, but it's a vital part in the product in general. Try again to have a sequence of the manufacturing processes in the production system. The material handling is going to be necessary to move the parts between different machines. Without it, we're going to have a slower, inefficient production process. Now, let's give me an example about the manufacturing process for the car once again. You all remember the view of seeing a line of production. Actually, they call it production line, and that was invented by Ford. And instead of working in small groups, he decided to move the chassis on a conveyor belt. The people will start to add the parts while the car is moving. So the chassis is going to be fed at the entrance of the conveyor belt, and at the end they are going to have a full car. This actually has been done because they use an efficient material handling system. Start to move the material from one side to another. Every station on this production line have an efficient material handling system, so they get to receive the parts on time when they need it. So usually the material handling system is going to be within the part of the facilities. So the production system is going to be consist of enterprise and the factory level. The material handling system is going to be within the factory level. That's for the production process. Still, for the logistic, for example, I'm going to have all my part from the external supplier. This is not going to be shown here, but it's going to be part of the production process. So once again, the section we're going to have today is going to be introduction to material handling equipment in general. That's something we've done earlier. The material transport equipment and the analysis of the material transport systems like the AGV and the retrieval system. So once again, the definition of the material handling system, as we mentioned earlier, is going to be the process of the moving, the storing, the protection, and the control of the material throughout the manufacturing and the distribution process, including their consumption and disposal. That's the definition according to material handling in the history of American society, they just simply define it as that. Usually estimated to be about 20 to 25% of the total manufacturing labor cost in the US. And this proportion, of course, is going to be varies depending on the type of the production and the degree of the automation. Car industry is heavily based on the material handling. The mining is heavily based on the material handling. The handling must be performed with the safety for the material and the workers, the efficiently, because otherwise going to be an extra cost, at low cost, at timely manner, accurately, and without damages to the material. Now for the timely manner and the low cost, I think that you heard about the excuse that the company and the governments usually give you about the logistic. They always get to say, oh, the price has went up because of the logistical problem. Now what do we have is, we have inefficient, higher cost, and wrong timely manner material handling system. That's what we have. And that's actually what caused the prices, in addition to degree of controlling the market. So for the logistic is concerned with the acquisition, the movement, the storage, and the distribution of the material and the product, as well as the planning and the control of these operations to satisfy the customer demand. Logistic can be classified as the external logistic, which is transportation of the material through the overseas. And we have the internal logistic, which is material handling and the storage within the facility. So for the external logistic, like for example, shipping of the coal to China, or shipping of the oil to China, or for example, purchasing the oil from overseas. So this will be a logistical process, transportation and related activities that occur outside of the facility between different geographic locations. And we have 5 traditional modes of the transportation, which are going to be the rail truck, the air, the ship, and the pipelines. For the internal logistic, if you are going to bring the coal and you deliver it to China, they have to store it. This will be temporary storage at the port. Then they have to move it within the port to a place where it's going to be loaded to the truck. And then once again, it's going to be an external logistic process. So these are some examples about the external logistic, where it's going to be away from the facilities. And this is the board which is going to do the internal logistic process. The categories we have for the material handling equipment going to be first material transport equipment, the storage that we learned about it last week, the utilizing equipment, which refers to the containers to hold the materials as a unit load, and the equipment used to load and packaging of the containers. And finally, the identification and the tracking system to identify and keep a track of the materials being moved and stored, and this will be very important. If you work in the future, if you're going to work in a factory, you will see that they always going to have a certain amount of storage of the raw material. Especially nowadays when we have the COVID and we have the problem with the logistic, once again, the supply chain management, we cannot simply depend in these conditions on what we call the just in time. We have to go back to the concept of the just in case. Now, just to remind you, for the students who've done the advanced manufacturing earlier, about what the just in time and the just in case. The just in time, that's mean you are going to order the material, is going to be arrived on a certain time or date, and then you are going to start the production process exactly when the material is going to be arrived. So in such case, you are not going to have a permanent storage for the material. You're only going to have a buffer storage for the material. So that's when you are going to get the material arrived in one patch, and you can use this material for 1 week. You make 1 day before the week going to be over to fill the pin. Now, when we say the pin, because we have something in this stock called the pins. We have pin A and pin B. We start to use this material. We're going to reach a certain level. We should have the other material to be arrived. So we're going to keep filling and emptying the bins until we're going to finish the production of the whole patch. Some design construction we have for the material handling that we discussed earlier, which were the material characteristics, the flow rate, the routing, and the scheduling, the plant layout, and the unit loader principle. This, of course, is going to depend on what the material we're using and what we're going to use it for. If I'm going to have the, for example, let's talk about the sand. If I get to sand for plastering operation in the construction process, I'm not going to order it by huge quantity. I don't need to mix it continuously. We're going to mix it by a small amount. So I can bring it as a unit load, just bags. I get to store the bags on the side, and whenever the worker is going to need to do the work for one place, they're going to grab what they need and mix it with the concrete and do the plastering process. But if I'm going to do the casting for the whole building, I'm not going to bring the sand in bags. I'm going to actually bring it in a silo and do the mixing and do the casting process. Now, the same thing for the plant layout. If I'm going to have continuous feeding of the materials, I need to be a raw materials. If I'm going to have by pieces, then I'm going to need as unit load. The material characteristic that we mentioned earlier is going to be affect the type of the transport and the storage of the equipment required. So if I'm going to have the material is going to be solid, liquid, or gas, of course I'm going to have a different material handling system. For the solid, I can use the conveyor belt or screw conveyor. For the liquid, I need a piping. For the gas, I get to need gas cylinders and sealed gas piping. The size is going to be small, it's going to be big. It's also going to be affect the weight, which is going to affect the density. The shape of the particle is going to be long, flat, or bulky. The condition of the material should be staying hot or should be staying cold, wet, dry, and the dirty effect on the material. Some material have risk of the damage. For example, it can be fragile, brittle, or sturdy. And finally, the safety risk of this material. We are always going to have something like the sheet we have for the risk assessment, and we're going to take these things. Is this material going to be exclusive? Is it flammable? Is it toxic? Is it corrosive? So we need to know where we're going to save it and for how long, and what will be the precautions we need to follow. Now for the flow rate, routing, and the scheduling of the material, of course you know that the flow rate is the amount of the material moved per unit time. How many kilogram or how many tons we need per hour. How many liter we need per minute. Okay, how many pieces we need per hour, and so on. So whether the material must be moved in an individual unit or as patches or continuously in the pipeline, we always need to know what will be the flow rate required for our production rate. For the routing, is the pick up and the drop off location, where we're going to put it within the place. How much distance we're going to move. What will be the routing variation? So how many times that we are going to move to a distant, certain location within our facilities. And also the condition along the route, like the surface, the traffic, and the elevation of the storing area. Now, finally, for the scheduling, which is going to be timing for each delivery. You need to specify when the delivery is going to be required. That's what we call the just in time. Thus, you are going to save the cost for the storage, and also you're going to avoid what we call the time consolidation effect. So the material is not going to be stored for a long time, and this will make it actually under the effects of being spoiled or damaged. Also, the use of the buffer stock to mitigate against the late deliveries. So once again, we try to avoid having the permanent stock. We always try to have a buffer stock. That's not going to be last for a long time. It's only going to be for a limited time. And once again, we're going to save the space required for the storing area. And also we are going to keep the material always fresh for our application. When I say fresh, it doesn't have to be food. Just imagine that you are storing a steel bars. Now these steel bars, you're going to leave it for a long time. It's going to get rusted. So that's why we need to always keep the material fresh, and that's why we need to do buffer storage instead of the permanent storage. So the most important thing is going to be the scheduling. Time of each delivery should be done. Now the other effect is going to be the plant layout. So the material handling equipment consideration must be include the plant layout design problem. Now plant layout, we remember that we described, for example, the production line is going to, of course, going to have a different need rather than the cells, or rather than the crude manufacturing. So the correlation between the layout type and the material handling equipment is going to be as follows. If again to have plant layout is going to be a fixed position, that means all the machines or all the equipment is going to be fixed. Then we need to use the cranes, the hoist, and the industrial trucks to move the material. If we're going to have processes, then we're going to use the hand trucks, the forklift trucks, and the AGVs. For the products, we're going to need the conveyors for the product flow, and the trucks to deliver the parts to the stations. Now for the what we call the utilizing, as the unit load is the mass that to be moved or otherwise handled at one time. You can simply fill a box with the material and you say, okay, now we have this box. It's contain, for example, 10 kilograms of the item. Just give me a second. Now, what the reason for using the unit loads in the material handling? Because simply we can put multiple items to be handled at the same time. It's required a number of the trips is going to be reduced, loading and unloading times are going to be reduced, and the product damage is going to be increased. And for the containers like the wooden pallet, which is the most common one, we're also only going to pelting the things on the top of it, which we're going to wrap it, so we are going to prevent the falling of it, and we're using the forklift to carry it. If the thing's not going to be wrappable, then we can use the pallet box or the tooth box for the smaller. Handling transport equipment, we said that we have the industrial trucks, the automated guided vehicles, the monorails and the other rail guided vehicles, the conveyors, belts, and this can be a conveyor rollers, and we have the crane and the hook. So we mentioned in the lecture number 1, trucks can be non-powered and can be powered. Non-powered, that means can be pushed by the human worker, and the powered one is going to have a certain type of the for example, motor, electrical motor, and thus is going to be guided with less effort. So an example of that, the non-powered industrial trucks, the two-wheel hand trucks, the four-wheel dolly, and we have the hand-operated loader truck. For the wheat forklift, we have like the power trucks, which is the forklift truck, is going to have a drive unit. Usually is going to be operated by electrical, need to be charged, of course, and then it's going to help the worker by using less effort to the material. We also have the forklifts, which can be once again electrical or operated by the natural gas, widely used in factories and warehouses. Capacities can be based between 450 kilograms up to 4,500 kilograms, and the power source includes onboard batteries and the internal. And we have the power tracks like the town tractor, and this actually can be very easy. We have the tow tractor and the trailer, designed to pull one or more traveling carts in the factory and warehouses, as well as for the airport package handlings. Again, this can be work with the batteries, or it can be having the Now, we're going to discuss briefly about some of these technology like the now for these students who work in beauty asset projects like the race car or the um, autonomous car, we have online here, okay? Because online is working on the in one of these projects. So anyway, the automated vehicle, guided vehicles actually has been started with the material handling. Later today, they start to design the autonomous car to be used for the public transport. In both cases, the concept is going to be the same. The vehicle is going to have a programmable unit and certain sensors, and it's going to follow a certain path during its material handling process. Guided vehicles system, or we'll go the AGV, automated guided vehicle system, is a material handling system that uses the independently operated, self-propelled vehicles guided along the defined pathway and the facility floor. So it's going to be moving. We have once again defined pathways, which can be a simple white line on the floor. And it's going to have the light sensors sending the light and reflected back. Always going to follow the white reflection and go through the path. It was programmed to stop at certain stations and do drop in or pick up the material at these stations. The types of the AGVs we have are first driveless train. We can have the pellet tracks, and we have the unit load AGVs. For all, the concept is going to be the same. The main difference is going to be how the load is going to be mounted. Driveless automated guided train is going to have drive wheel in the front, and it's going to pulling the trailer tracks. This was the first AGV to be introduced back in 1954. Common application is going to be moving all the heavy payloads over long distance in the warehouses and factories without the internet alone. For the AGV pellet track, you can see it's going to work as a forklift. It's used to move the palletized loads along the predetermined roads. Vehicle is backed into a load pallet by the worker. The pallet is going to be elevated from the floor, and the worker will drive the pellet track into the AGV guide path and the program's destination. For the unit load carrier, it is going to be used to move the unit load from the station to station, and often is going to be equipped with automatic loading and pallets and the tote bands using roller conveyors, moving pallets, or the machinized left platforms. So you can see that the unit load carrier is going to be the most independent types of the AGV. Actually, it's one of the also to be one of the modern one, which has been introduced back in 1980s. The AGV applications for the driveless train operations is a unit of large quantities of the materials over long distances. It doesn't have to stop and unload during. For the storage and the distribution, by the movement of the pallet load between the shipping, receiving docks, and the storage racks achieved. Simply line operations, where the movement of the car bodies and the major sub-assembly like the motors through the assembly stations can be achieved. And finally, we can use manufacturing systems for the movement of the work parts between machine tools. Other applications can be miscellaneous, like the mail delivery and the hospital supplies, where simply you can actually load the AGV from the medicine storage, and it's going to take it to the different wards and distribute it. Now, the technology of the is usually built on the pathways that are going to be defined, and the vehicle are going to be controlled to follow these pathways. As I mentioned earlier, technology started first with the wires. then started to follow a white line on the floor. Later it's changed to yellow. And we have the self-guided vehicles. What are the three main technology we have so far? The embedded guided wires, it's going to follow the wire which having the current that generate the electromagnetic field. We have the sensors which are going to follow the electromagnetic field for the wire which is buried under the floor, and thus is going to find its way. So if I get to have, for example, a T junction on the floor, if I get to operate the one to the right, the machine the AGV will go to the right. If I get to activate the one to the left, the machine will go. So the paint strip actually is an optical sensors is going to be used instead of the electromagnetic sensors. So the optical sensor is going to send the light on the floor, reflect the light. The white strips on the floor, or the reason why it's yellow, the yellow strips on the floor is going to reflect the light back. So everything outside this line area is going to look black, and in the middle is going to be white. And thus the sensor will always going to guide the vehicles to follow this white line. The more advanced technology is going to be the self-guided vehicles, which is vehicle use combination of the depth reconing and the beacon located throughout the facilities. For the reconing, is the vehicle going to count the wheel turns in direction to move without guidance. So it's something like when you walk in the dark, in a place that you know, and you say, okay, now I get to walk for 5 steps, and I get to turn to the left. Another 10 steps in the direction of the left, then I'm going to stop. That's a logic thing. So it's going to be counting for the wheel returns. Of course, the wheel is going to have a certain circumference, and this circumference, that means, for example, is going to be equal to 1 meter. So every full turn, that means that the machine, the AGV, has moved for 1 meter in this direction. For the beacons located throughout the facilities, where the vehicles get to use the triangulation to compute the location. Something similar to what we have in the case of the, we call it the navigation system we have in the cars. I forgot what they call it, but anyway, it's something like, again, to have multiple signals, give the coordination in the factory or in the location. And the equipment on the machine is going to tell the machine the location instantaneously by doing a certain calculation between the different things we have in the facility. So we have two aspects of the vehicle management. The first one is going to be, the other one is going to be vehicle dispatching. So for the traffic control, it's just to minimize the interference between the vehicles and to prevent vehicles from down. So we're always going to have traffic control to prevent the machine to be on the same place at the same time. So this can be done by having the forward sensing on, so they're going to stop before it's going to hit the other one, or having the zone control. In the zone control, the programming is going to prevent vehicle to go to the other zone. So each AGV is going to be limited between 1 or 2 more zones at maximum. The vehicle dispatching, and this can be done by using the onboard control panel or remote control stations or the central computer control. So let's start to explain the zone control. So you can see that we have 3 AGVs. And for example, the AGV1 is going to be specialized work in the zone A. The AGV2 is going to work on the zone B, C, and the AGV3 is going to work. So what we can have here that, for example, the zone C is free. So vehicle 2 is blocking from the entering this zone as long as the vehicle A is there. Others can go to the zone C as long as the vehicle 3 is not there. So only the free zones are going to be available for the vehicle to move. The vehicle safety is going to have the control of the travel velocity of the AGV, which should be always slower than the walking speed of the human. So you're always going to give him the chance to escape if the machine is going to approach. You can have the automatic stopping, where the vehicle is going to stray from the right path, and this can be done by station distance. You can have the obstacle detection. If you have sensor in the front, ultrasonic sensor, so if another vehicle or a human standing in the vehicle will stop moving. You can have the emergency bumper where they brake the vehicle when the contact is going to be made by the object. Something like where they're going to have the contact sensor. So when the bumper is going to be pushed a little bit, the signal will be sent to the motors and it's going to stop immediately. The warning lights is actually part of the safety procedure for the AGVs and the warning sound as well. Now, I'm not sure if the final video is able to. One second. Stop sharing and a chance to. Okay, so once again, we can see this will be a test for the AGV safety system. Now, the lines here are going to be the path that the AGV to be followed, but I'm sure that the AGV we're going to see in the next video is going to be self-controlled vehicle. So you saw that when the worker obstructed the machine, the AGV, to stop moving until the path was clear and resume the movement again. Now we're going to see some brief analysis process, simple analysis process for the vehicle-based system. Usually we use the chart we call the form 2 chart. So when to start and where do I get to stop and what will be the activity I get to achieve that, it's going to be charted. So this chart showing the flow rates, the loads per hour, which is the value before the slash, and the total distance in meter, which is going to be the value after the slash, between the station and the layout. So let's use my pen here. So we're going to move from the station number 1 to the station number 2. Of course, they're going to move to station number 1 because it's the same station. So from 1 to 2, we're going to have 9 parts to be moved per hour, or 9 loads per hour. And the distance to be moved is going to be 15 meters. From 1 to 3, we're going to have 5 loads per hour, and the distance is going to be 120 meters. From 1 to 4, from station 1 to station 4, 6 loads per hour, and the distance total is going to be 205. And there is no passes from 1 to 5. Now, from 2, we have 9 per hour. It's going to move to the station number 5. 9 loads from the station number 2 is going to be traveling back to the station number 5. Distance is going to be 80 meters. Now we can consider that every station is a different machine. Just an example. From the 3, we are going to have 5 units per hour has been sent from the station 1. 2 of them will go to the station number 4, moving for 85 meters. And the other 3 will go to the station number 5. Number 4 actually received 6 units from the station number 1, 2 from the station number 3. Let's make it totally 8. And these 8 are going to move to the station number 5, passing the distance of, traveling the distance of 85 meters. Now another way to show the flow rates other than the from to chart, which is going to be the network design diagram design. So the same process is going to be defined here. We have 1, 2, 2, 9 units per hour passing 50 meters. From 1 to 3, 5 loads per hour passing 120 meters in this way. From 1 to 4, 6 loads per hour traveling for 205 meters. Then from that I get to all moving to station number 5, either directly or through the station number 4. Now we can use these charts and the diagrams to make the analysis for the efficiency and the number of the vehicles required to achieve this performance. So the AGV analysis is going to be mainly the delivery cycle time calculation. This will be the first thing. So the analysis will begin first with estimating the total time in the delivery cycle of the vehicle on average. And this is simply going to be by ignoring the effects of the traffic congestions. So we're going to consider that the truck or the vehicle is going to move totally without any waiting time. The cycle time can be calculated with this equation. The cycle time or the TC, delivery cycle time for one vehicle in minute per delivery is equal to the TL, which is the loading time in minute, plus the LT divided by the VC. The LT is the average distance traveled while loaded per delivery, and divided by the velocity of the vehicle. The VG is the AGV speed, which is shown to be a constant in feet per minute or meter per minute. And of course, if the LD is the loaded travel distance, the LE is going to be the unloading time, sorry, TU, and the LE is going to be the average distance traveled while it's empty vehicle. Now, when I say that it's going to be loaded or empty, if we go back once again to the diagram here, we sent 9 loads per hour to the from 1 to 2. Now the machines are not going to be staying at 2, sorry. It's going to be traveled to a lot of distance. So it's going to come from here to here, loaded. Then it's going to travel from 2 to 5, loaded. 5 to 3, sorry, 5 loads from 1 to 2, 1 to 3. And then we're going to have them split it to go to the number 4 and number 5. Number 5, we're going to have 8 units going because simply we're going to have more truck waiting here. Now the trucks here is going to be all arriving loaded, but need to be unloaded and travel as in empty trucks. So the distance to be traveled, this one is going to be for the loading, and then from 5 to 1 is going to be distance for the unloading. So this will be at the beginning of using the TC value for a further analysis. So once again, this will be one of the equations we're going to use in the next example. And we're going to have at least one question in the assignment number 3. Don't rush over the assignment number 3, still have long time to go. And after that, we're going to be able to calculate the other parameters. So we need to do some other assumptions later. For example, we are going to consider what are the factors affect the delivery cycle time, which is the availability of the vehicle, the traffic congestions that we actually ignored earlier, and the efficiency of the manual elements. To calculate the value of the AT, so the AT is going to be equal to a 60 multiplied by the availability multiplied by the TF, which is the traffic congestion, multiplied by the efficiency. The unit is going to be 60 minutes per hour per vehicle. 60 minutes per hour, 60, minute per hour per vehicle. Now, the rate of the deliveries we have for the AGV, rate of delivery is equal to the AT has been calculated, divided by the TC calculated earlier. And first we can find the number of the vehicles required for the operation, which is going to be equal to the RF divided by the RDV. The RF is required deliveries per hour for the station. Okay, so these are a list of the material handling analysis. We just took the simplest one. We said that the VC is going to be the average speed of the vehicle. The VE is going to be the vehicle of the empty speed, if we consider that the vehicle is going to be lighter. The TH is the load handling time, how much time is required to put the loads on the machine. And the LD is going to be destination distance as a loaded vehicle. L is the empty move distance. TF is traffic factor, which should be equal to 1 or less. And the EH is going to be handling system efficiency, A, the proportion of the time vehicles is going to be operational. AT is the available time in minutes per hour per vehicle. And the E is the worker efficiency. The RDV is the rate of the deliveries per vehicle. The NC is number of the carriers required. The RF is specified the flow rate of the system in deliveries per hour. The TC is going to be delivery cycle time. TL is the time to load and unload the station. And the TU is going to be time to unload at load station. And WL is going to be the workload. Now, the list of the equation you are going to use in your calculation has been tabulated here for easier than going back to the slide. So we're going to use this equation to make our fast analysis for the AGV example. The next AGV example is going to be very simple. We're going to have one AGV moving between loading and unloading station, and it's going to pass a certain path as loaded and a certain distance as unloaded. We're going to have a certain assumptions to do the calculation for the number of the vehicles required to achieve the hourly load. Now, this is our first example. So what we can see here, we have the loading station here and unloading station here. We have AGVs transporting the material between the two stations. The distance between them, you can see that distance from side to side is 55, the height is 40, the distance from here to here is 20, so we can calculate what will be that distance. Okay, that distance simply is going to be equal to 55 minus 20, that's going to make it 35, times 2 is going to be 70, plus 40. This will be the loaded distance. Okay, 110. first side here is going to be the empty traveling distance. 20 plus 20 is 40, plus 40 is going to be 80. So the LE is going to be 80. Okay, so let's read about that. We consider that we have the AGV layout is shown in this figure. The vehicle travel counterclockwise, as you can see, around the loop to deliver the loads from the load station to the unload station. The loading time at the load station is 0.75 minutes. Loading time, TLU. The unloading time at the unload station is 0.5 minutes. TU. The following performance parameters has been given. The vehicle speed is 50 meters per minute as a VC. The availability A is 0.95 or 95%. The traffic factor is 0.9 TF or 90%. The operator efficiency does not apply, so again to consider it to be 1. Now what we need to do in mind again to be the following. First, the travel distance loaded and empty. I just said that earlier. The ideal delivery cycle time, the TC. The number of the vehicles required to satisfy the delivery demand. If we are going to have in total 40 deliveries per hour must be completed by the AGVs. So we need to know how many vehicles are going to be used to achieve 40 deliveries every hour between the loading and unloading station. Now we have been given the AGV layout and we know the flow rate, and we need to do some calculation. First thing we are going to do is we are going to list the information we have. We list the parameters to find the outcome. So the parameters were once again the loading time, the unloading time, the vehicle speed, the availability, the traffic factor, and the distance moved loaded and the distance moved unloaded, and the efficiency of the travel. So once again, I think this one is going to be actually very easy compared to what we are going to have later, and we're going to do the calculation for our analysis. First, we are going to ignore the effects of the slightly shorter distance around the curves at the corner of the loop, and the values of the LD and the LE are going to be really determined from the layout to be 110 and 80 meters respectively. Calculate the TC value. TC is going to be equal to the loading time, TL, plus the unloading time, TU, plus the loaded distance divided by the velocity of the vehicle, plus the unloaded distance divided by the velocity of the vehicle. The WL is going to be equal to the RF multiplied by the TC. The AT is going to be equal to the 60 multiplied by the A multiplied by the FT multiplied by the efficiency. We said that this value is going to be equal to 1. The availability is given as 0.95. The TF is given as 0.9. So we can calculate the AT value directly. Here, the TL known, the TU known, the LD known, the VC known, and we can calculate the TC. The number of the carriages or number of the vehicles is going to be equal to WL divided by the AT value calculated from this equation. So let's see how we are going to substitute the values to get the results. Okay, so first, for the ideal cycle time, the TC is going to be equal to 0.75 minutes for the loading, plus 110 divided by 50 meters per minute, plus 0.5, which is the unloading time, plus 80 meters divided by 50. So the TC is going to be equal to 5.05 minutes first. Now we need to compute the workload, WL. WL is equal to the RF, which is the number of the loads required per hour, 40, multiplied by the TC. And we're going to get that the workload time is going to be equal to 202 minutes per hour. Now, how we can achieve 222 minutes per hour? Definitely we need more than one vehicle, where the maximum we're going to achieve is going to be 60 minutes per hour for each. Now, we know the TC, we know the WL, we can calculate the AT. So once again, we say it's going to be 60 multiplied by 0.95 multiplied by 0.9. And the answer is going to calculate the AT, and we're going to get 51.3 minutes per hour per every vehicle. So now we are going to need 202 minutes per hour to achieve the 40 loads. And the available time per every vehicle per hour is going to be 51.3. So to know the number of the vehicles, we're going to divide the WL by the value of the AT. And we're going to get 3.94 vehicles. Of course, if we're going to have fraction, we need always to round it up. So even if this number is going to be 3.07, we're going to say we need 4 vehicles to do the job. We never get to go down. Of course, there is no fraction vehicle. Now, even more complicated example is going to be this one. You can see that we are going to have multiple stations, multiple loops, and thus we are going to have even more complicated processes and analysis should be done. So in this problem, we are going to have the loading station is here. Our loading station is here. Let's see how the process is going to be done. Of course, these figures are going to give you the ability to calculate the loading and unloading distance. So the from to chart tell us the following. That we are going to move 9 loads from the station 1 to the station number 2. So from 1 to 2, okay, from 1 to 2, we are going to move 9 loads per hour, and the distance between them is going to be 50 meters. Of course, it's going to be 10 plus 10 plus 30. It's going to be 50. From 1 to station number 3, we're going to have 5 loads. That's going to be traveling for 120 meters every hour. From 1 to 4, from 1 to 4, we're going to have 6 loads, and the distance is going to be 205 meters. Now from there, the material is not going to go back to station 1. Instead of that, from the station 2, we're going to have the 9 loads are going to go to the unload, passing 80 meters in the way. From station 3, we're going to have 2 of the loads, 5 loads has been received, going to go to the station number 4, passing 85 meters, while the other 3 will go back to the station number 5, passing 170 meters. And from the station number 4, we are going to have 8 loads are going to be traveling to the station number 5, passing 85 meters in this way. So I need to do the answers for this process, and this will be a little bit So first we need to mine the LD for more complex AGV layout. This layout in the example shown in the figure, and we have the from to chart is presented in the table 1. The AGV includes the load station 1, where the raw bus are going to enter the system for the delivery to any of the 3 production stations, 2, 3, and 4. The unload station 5, we're going to receive the finished parts from the production station, and the load and the unload item times in the stations number 1 and 5 are going to be each 0.5 minutes. The production rate for each workstation are indicated by the delivery requirement in the table 1, and a complicating factor is going to be that some of the parts must be transshipped between the station 3 and the station number 4. The vehicles are going to move in the direction indicated by the arrow in the figure, and we need to determine what will be the average delivery distance, LD first. So once again, we are going to go back to the chart table and try to make the analysis. Now, we need to calculate the LD. And in this case, we are going to have more complicated process to the job. To determine the LD, the weighted average must be calculated based on the number of the trips and the corresponding distance shown in the from to the chart for the problem. So let's start to calculate. 9 loads. Each time, every load is going to be passing 50 meters. So we're going to have 9 times 50. We're going to have 5 each time. Each trip is going to passing 120 meters. So we're going to have 5 times 120. 6 times 205, 9 times 80, 2 times 85, 3 times 170, 8 times 85. So first we are going to have all the loaded travel distance. Now we are going to do the number of the loads in general. So the average number of the trips, the loads are going to be 9 plus 5 plus 6 plus 9 plus 2 plus 3 plus 8, which is going to be 42. So the LD value is going to be equal to 103.8 meters. That will be the average value. Now, I'm going to give you another example later. There's going to be something similar to the one we are going to have in the assignment question. And I'm going to encourage you to use the Excel sheet to do the work. I'm going to show you this example later. Now, this is just a simple example. You can use it to check your ability to use the equations. This one is quite simple. We have 40 deliveries per hour should be done. The velocity of the vehicle is 150 feet per minute. We have the average distance traveled per delivery is going to be 450 feet. The average distance traveled as empty is going to be 450 feet. The pickup time is 45 seconds. The drop-off time is 45 seconds. Traffic factor is 0.9. Determine the required number of the vehicles. Just to be the example number 1, assuming that everything that we don't have is equal to 1. So the availability is going to be equal to 100%, for example. The efficiency is 100%. So you can calculate the 80, which is going to be equal to the 60 multiplied by 90. The TC can be calculated from here. And the number of the deliveries is 40, so you can calculate the WT. Then you will find the number of the vehicles. Now, I think that I will stop the recording just to have a break. And during this break, we are going to have a discussion about some of the topics that we discussed earlier. Then we will go back to the recording once again in maybe 10 minutes. We don't have a lot.